This is a tropical cyclone rapidly organizing over the Indian Ocean, converting heat into a massive, rotating engine of kinetic energy. When these storms track northward, they funnel directly into the Bay of Bengal, making the lower Ganges-Brahmaputra delta one of the most vulnerable impact zones on the planet. The primary climate driver increasing this vulnerability is rising sea surface temperature. This chart tracks regional water temperatures against cyclone frequency from 1980 to 2020. As temperatures rise by 4 degrees, frequency scales up. Temperatures crossing 31 degrees act as a thermodynamic catalyst, allowing pre-monsoon cyclones to rapidly intensify before landfall. Today, regional coastal infrastructure is facing an increasing thermodynamic threat that standard historical defenses are struggling to mitigate. Spanning the Bangladesh-India border is the 10,000 square kilometer Sundarbans mangrove forest. Beyond its status as a UNESCO World Heritage Site, this forest operates as a macro-scale, unengineered coastal defense structure. The challenge lies in translation. Ecology is often viewed as chaotic, but civil engineering requires rigid, quantifiable parameters. By analyzing empirical geospatial data from recent cyclones, we can quantify the kinetic energy dissipation of these mangroves and translate it into mathematical parameters for structural embankment design. Ultimately, moving from qualitative ecological observation to quantitative engineering application is the true path towards sustainable coastal resilience. Researchers at the Chittagong University of Engineering and Technology utilized a natural experiment to measure this effect, comparing Cyclone Bulbul in 2019 and Cyclone Sitrang in 2022. Both tropical cyclones possessed similar offshore intensities, but followed divergent landfall trajectories. Cyclone Bulbul tracked directly through the dense vegetation of the Sundarbans. This interpolation map shows the deceleration of Bulbul. Wind speeds dropped from 60 knots offshore to 40 knots after passing through the forest. Cyclone Sitrang, however, bypassed the forest and made landfall in the low-vegetation Patuakhali district. In Patuakhali, Sitrang maintained dangerous wind speeds between 43 and 45 knots across a massive inland radius because it lacked a physical buffer. The geographical point of landfall significantly influences how much cyclonic kinetic energy is retained as the storm moves inland. To isolate the cause of this decay, analysts use the Normalized Difference Vegetation Index, or NDVI, to measure canopy density. The high NDVI values of the Sundarbans indicate a dense canopy, scaling up to an index of 0.60. By comparison, the Patuakhali region barely registers a maximum NDVI of 0.09. Cross-referencing wind speed drops with these density zones establishes a direct empirical correlation. As the cyclone penetrates deeper into high NDVI territory, moving from 0.36 to 0.46 density, the wind speed proportionately decays. The forest canopy is not a passive landscape. It is an active physical windbreak that absorbs and disperses kinetic energy. Beyond wind speed, the deadliest cyclonic threat is storm surge inundation. This map shows the flooded area within the Sundarbans during Cyclone Bulbul. The forest restricted flooding to 14.37% of the analyzed terrain. In Patuakhali, where the vegetation buffer was absent, the same storm inundated 37.58% of the district. This macro-level surge protection is caused by a micro-level mechanical feature, the structure of the mangrove roots. These are pneumatophores, dense, rigid, above-ground breathing roots unique to these mangrove species. As a massive storm surge pushes through this network, the water experiences physical resistance known as frictional drag. Modeling indicates that 1 kilometer of this forest reduces wave energy by more than 75%. This results in a measured 5 to 50 centimeter reduction in peak surge height per kilometer of forest. The unique root architecture acts as a hydraulic brake, restricting inland flooding to a fraction of what undefended areas suffer. Civil engineers at the World Bank use hydrodynamic modeling to turn these ecological drag coefficients into structural building codes. This is a standard coastal protection embankment without a natural buffer. The concrete wall must absorb the full, unrestricted stress of the surge. By placing a mangrove foreshore in front of the structure, the incoming wave height is attenuated before it ever reaches the wall. Because wave height is reduced by up to 55%, the required height of the concrete dike can be lowered by up to 0.30 meters. Reduced wave energy means the concrete slope revetment thickness can be reduced by 13 to 46%. Finally, wave shear stress at the toe of the embankment drops by 25 to 70%, preventing the erosion that often leads to foundational failure. Ultimately, relying on ecological friction allows civil engineers to safely downscale expensive hard infrastructure while increasing overall safety tolerances. These engineering models are now being applied to proposed afforestation sites along the Bangladesh coast, including the Kukri-Mukri polder and Polder 45 in Amtali. Establishing these belts provides a triple dividend: risk reduction, carbon sequestration, and local livelihood enhancement. The data demonstrates that mangroves are mathematically predictable shock absorbers. Integrating nature-based hydrodynamics into structural engineering provides an empirically validated mechanism for survival in a warming world.